Hey everybody, this is Mr. Bortnick for AP Calculus AB. We are in Unit 5, Analytical Applications of Differentiation. Today's topic is 5.11, which is solving optimization problems. Today is a calculator day, so please make sure you have your TI-83 or TI-84 available. And remember that when we're using calculators in AP Calculus, we use radian mode, and we always round to 3 digits after the decimal place. Enjoy today's notes. All right, welcome to 5.11, which is about solving optimization problems. Once again, a reminder that this is the second video in a pair of videos. The first video was in 5.10, and if you have not watched that, I encourage you to go back and watch that. It's the intro to solving optimization problems. And in general, we're going through the strategies for solving these optimization problems. The first three were what were covered in 5.10. So draw a picture if applicable and identify known and unknown quantities. Write an equation model that will be optimized, and then write your equation in terms of a single variable. Today's focus for 5.11 is going to be on 4 and 5, where we're bringing calculus into the mix. So how do we determine the desired max or min value with calculus techniques, and then determine the domain endpoints of your equation to verify if the endpoints represent a max or a min. So what we're going to do is we're going to go through a handful of problems that we started on our previous lesson. The first one was this problem that says what point on the graph of y equals the square root of x is closest to 5, 0. Now again, if we're trying to think about the distance, maybe we're saying it's somewhere over here, but if we want to find the precise value that's the closest, we're going to want to use these optimization techniques. Now in the previous lesson, we used the distance formula to say that the distance from this point to some arbitrary point on this line, so I'll say that this is d over here, is going to be equal to the square root of x minus 5 quantity squared plus x. Now again, if you did not watch the video from 5.10, I would encourage you to go back and see where that equation came from. But we are now at step 3, moving into step 4. So in order to find this max or min, we're going to need to take the derivative. And so since there's a square root here, I'm going to rewrite this expression as x minus 5 quantity squared plus x, all being raised to the 1/2 power. Next, I'm going to find d prime. So the derivative, using the chain rule for our equation over here, if we use the chain rule, that 1/2 is going to get brought down to the front. We've got this then x minus 5 quantity squared plus x, all being raised to the negative 1/2 power. Then we need to multiply by the derivative of the inside. So that is going to be 2 times x minus 5 plus 1. And so that's going to be the derivative of the inside part right here. And so if we want to simplify this, I'm going to rewrite this so that it doesn't have any negative exponents. This is going to be d prime is equal to 2 times x minus 5 plus 1, all divided by 2 times the square root of x minus 5 quantity squared plus x. Now, of course, we're looking for the closest value. So in this case, closest is going to make the distance d a minimum. And we know from our work earlier in chapter 5 that minimums and maximums only can occur, extrema can only occur at critical values, places where the derivative is equal to 0 or it's undefined. So I want to try to figure out, places where this is going to be equal to 0 or it's undefined, which really for this case means, we're looking at places where this numerator is going to be equal to 0. There's no value that we can plug in that would make this a negative value or make this equal to 0. So we're just looking at the numerator being equal to 0. So to find the critical value, we're going to set 2 times x minus 5 plus 1 equal to 0. So then we're going to say 2x minus 10 is equal to negative 1. So 2x is equal to 9. And then we're going to say that x is equal to positive 4.5. So what does that mean? This is the only critical value. It's the only place that there can be a maximum or a minimum. So because of that, this must be the minimum for this. This must be right when x is 4.5. I'll erase what we've got right here, but right when x is 4.5 at this point right here, that is going to be where the minimum occurs. And so this distance here is going to be the shortest possible distance as opposed to like any of the other ones that we've got here. So what is the coordinate? They're saying what point on the graph, not just the x value. We should plug that back into our original equation, y equals the square root of x. That's going to be at the point 4.5 comma the square root of 4.5. And that is going to be the exact spot that is closest to 5 comma 0 on that function. Nice. Let's talk about number 2. Two towers are 30 feet apart. One is 12 feet high and the other is 28 feet high. In our previous lesson in 5.10, we drew a picture for this and we found that the distance equation for this is equal to the square root of 12 squared plus x squared plus the square root of 28 squared plus 30 minus x quantity squared. So that is our distance equation. And we're asking here where should we be using the least amount of wire. So we're trying to find a minimum here, which again, maximums and minimums can only occur at critical values. So we need to find the derivative and we need to find out where that's going to be equal to 0 or it's undefined. So first off, because there's square roots, I'm going to rewrite this so that there are no square roots. We're going to rewrite these as 12 squared plus x squared to the 1/2 power plus 28 squared plus 30 minus x squared to the 1/2 power. And then now we're set up to take our derivative using the chain rule. So d prime by the chain rule is going to be 1/2 times 12 squared plus x squared to the negative 1/2 power times the derivative on the inside, so times 2x, plus, doing the chain rule here on this second piece, 1/2 times 28 squared plus 30 minus x squared to the negative 1/2 power times the derivative of the inside. The derivative of 28 squared is, since that's a constant, is 0. And then the derivative of 30 minus x squared is going to be 2 times 30 minus x to the 1 times negative 1, since the derivative of negative x is negative 1. So if we want to rewrite this, again, I'm going to try to rewrite this in such a way that we don't have any negative exponents. We're going to have, let's see, 2x. So d is equal to 2x divided by 2 times the square root of 12 squared plus x squared. Not a ton of room here. My apologies. And then plus, let's see, negative 1 times 2. So negative 2 times 30 minus x to the 1, all divided by 2 times the square root of 28 squared plus 30 minus x quantity squared. So maybe a little bit tough to see, but this is how we would write this with fractions and without these negative exponents. Now, of course, again, we're trying to find critical values. We're trying to find places where this is equal to 0 or it's undefined. Because we're adding these things that are being squared here, these can't be negative or 0 here. So neither of these could be undefined. We're really just looking for places where this derivative is going to be equal to 0. And let me mark, this is d prime, not d. But I'm not going to do this by hand. We certainly on some of these problems on the AP exam, we're going to have access to a calculator to do it. So I'm going to show on your graphing calculator what we would do in order to do that. So let's switch over to that graphing calculator now. All right, so now that we've got our calculator up, what we can do is we're going to go to our y equals screen. And we're going to try to graph the derivative. Again, I'm trying to find out where the derivative is equal to 0, so that's going to be places where this graph crosses the x-axis. Since I'm using the TID4, I'm going to take advantage of the functionality that deals with fractions I'm going to hit alpha and y equals to get to this F1 menu. And then we've got this numerator being divided by the denominator. So I'm going to hit enter for that. And it's going to give me this nice little fraction symbol so that I don't have to deal with division issues on this. So in the numerator, we've got a 2x. In the denominator, it looks like we've got 2 times the square root of 12 squared plus x squared. So that is all in the denominator. And then I'm going to hit plus, since we're adding, and I'll go and do a second fraction. So I'm going to hit alpha, and then y equals to get this n divided by d, and we'll do it again with the second part of this. So this appears to be negative 2 times 30 minus x. That is being divided by 2 times the square root of 28 squared plus the quantity 30 minus x squared. All right, so we have this expression here for, or this equation here for the derivative function. Before I jump right into just the graph, I'm going to take a look at the window for this. So my window, in this case, you know, if we're looking at x values, we know that these towers are 30 feet apart. And so I can place, so x is the distance from the stake to one of the towers. I can place it anywhere from 0 to 30 feet away from the first tower. So I'm going to move down and go from 0 to 30 in my x values. Again, that makes sense because it can't be greater than 30 since it has to be between these two towers that are 30 feet apart. And then I'm going to zoom in pretty close to the x-axis. So I'm going to make my y min like -1 and y max 1. This is again because I don't really care how high or low the graph goes. I'm curious to see where the derivative is equal to 0, which is places where it would be crossing the x-axis. So let's graph it and see what we've got. All right, so we can see, you know, this is a graph of our derivative function that we typed in. We can see that something is happening at whatever x value this is. You know, I can maybe count the tick marks, but I want to know exactly, so I'm going to have it calculate it just in case it's a decimal. So second, and then this trace button to go to the calculate menu. I'm going to know where this function is equal to 0. So I'm going to go to 2, and I'm going to hit enter, and I'm going to get as close as I can to the actual place where it crosses the x-axis, and it's asking me for left bound. So I'm going to hit left a few times. I'm going to hit enter. I'm going to go back to the intersection point where it crosses the x-axis. Now it's asking me the right bound, so I'm going to hit right a few times on that cursor and press enter. And it's asking me to guess. So I'm going to go back to the intersection point and press enter one last time. And it turns out that it's crossing at exactly x equals 9. So that seems like the best place that we can place the stake to have the least amount of wire. Let's go back to our main problem. All right, so using our calculator, we just saw that the best place to place this wire is going to be at x equals 9. So 9 feet from the 12-foot high tower is going to cause us to have the minimum number of the minimum amount of wire used. Let's go on to number 3. So a particle is traveling along the x-axis, and its position from the origin can be modeled by x of t, where x is in centimeters and t is in seconds. On the interval from 3 to 9, find when the particle is farthest to the right. So thinking about particle motion, this particle is moving along the x-axis. So moving to the right in this case is going to be essentially finding, if it's farthest to the right, it's going to be finding a maximum here. If we're going farthest to the left, that would be a minimum in this case. So let's take a look at the derivative of this function. So the derivative here is the velocity. That's going to be 3t squared minus 30t plus 72, which looks like we can factor out a 3. That's going to be 3 times t squared minus 10t plus 24, which we could further factor and say that this is going to be t minus 6 times t minus 4. So this is going to have then critical points, critical values at t equals 4 and 6. And so those are the possible places here where this function could possibly have maximums or minimums. So in this case, because they gave us a closed interval here, they gave us the interval from 3 to 9, it would make the most sense for us to be trying to find the absolute maximum here. And we learned earlier in this chapter about this thing called the candidates test, where we can test the critical values, but we also need to test the endpoints as well. So what I'm going to do over here is I'm going to make a little table. Again, we're doing some review here on the candidates test from earlier in this chapter. And my table is going to look like this. I'll have my t here on the left side of the table. On the right, I just want to know what the output of the function is, x of t. And I'm going to use the t values of 3, 4, 6, and 9. Again, these t values came from the two endpoints of my interval and from my critical values here. We are going to want to plug in and find out what the x of t is. I'd encourage you to use your calculator in order to do that. But, I'll just put our answers here for this. We've got 99, we've got 103, we've got, looks like 99 and 153 here for this particular one. So it looks like the maximum value is occurring, maximum output is at 153 when t is equal to 9. So t equals 9 is that max. So it is furthest to the right when at 9. For B, on the same interval, so from 3 to 9, what is the particle's maximum speed? So we need to remember again from earlier in this chapter that speed is the absolute value of velocity. Right? It's velocity without direction. And so if we're going to find the maximum speed, we want to take the derivative of the speed or velocity function in this case. So the derivative of velocity is a of t, and so that looks like that's going to be 6t minus 30. And we want to find possible places where this function, maybe has possible points of inflection, but really I want to see where this derivative of velocity changes signs. So 6t minus 30 is equal to 0, so 6t is equal to 30, which would be a t is equal to 5. Now again, because they gave us an interval, which is from 3 to 9, we do need to test the endpoints as well. So once again, I'm going to do the candidates test and just see of the candidates being the endpoints and the critical value of the velocity, which is at t equals 5, which one is going to be the largest since we're trying to find the maximum. So our t is going to be on the left. On the right, we're going to have our a of t, the acceleration. Well, actually, no, we're going to do v of t. And I'm going to plug back into our equation from part A, our velocity here. And again, the points that we're doing are 3, 5, and 9. The critical value, the derivative of the velocity, which is equal to 0, and then also the two endpoints. Again, I just used my calculator on this, but if we do that, we get the velocity is 9, -3, and 45. Now here's the sort of the weird part for this problem. They didn't ask about the maximum velocity. They asked about the maximum speed, which means, when we plugged into the velocity equation, these are velocity values. So the 9 is going to stay 9. The -3, we can't have negative speed. That's going to become +3. It's just going 3 in the negative direction. And then 45 is 45. But of these, the largest clearly is 45. So I would say that the maximum speed is going to be 45. And what do we have? We have centimeters and seconds. So 45 centimeters per second is the maximum speed. And that occurs at t equals 9. But they didn't ask that. So that is our answer for this particular problem. And it looks like that's it for our examples. As usual, we've got practice for you to try, and the solutions are posted. Come on to class and ask some questions if you've got any questions, or come to office hours. And good luck on your mastery check. Hope you have a great day.